On a Saturday in early August, a machine rolled off a production line in Wuhan that engineers have been trying to build in one form or another for decades. It doesn't look like much in the photos. A long cylindrical body, a massive circular cutterhead at the front, cables and conveyor systems running down its length. The same basic silhouette as any large piece of tunneling equipment you might glance past on a construction site. But inside that unremarkable shell sits something that's never existed before anywhere in the world. A single machine that can bore through solid rock, blast through it, or switch seamlessly between both, depending on what the ground in front of it demands at any given meter of the tunnel. China Railway Science and Industry Group, working with Tsinghua University, calls it the BBM, short for boring and blasting machine, a name that sounds almost deliberately unglamorous for a piece of equipment this genuinely novel. In laboratory testing, it improved tunnel excavation efficiency by 30% compared to conventional tunnel boring machines. That's not a marginal gain. In an industry where a single-stalled tunnel boring machine can delay a project by months and cost tens of millions of dollars in idle, labor, and equipment, it's now headed for its first real deployment at a pumped storage hydropower station, where engineers will spend months collecting field data to see whether that lab number holds up underground in real rock under real pressure, with no do-overs if something goes wrong. That might sound like a fairly narrow engineering story, the kind of niche industrial news that stays inside trade publications. It isn't. Nearly everything humans build below ground, subway systems, water pipelines, mining shafts, hydropower diversion tunnels like the massive ones currently being carved through the Himalayas for China's new megadam, runs into the exact same problem this machine was built to solve, rust that refuses to behave the way engineers expect it to. Solve that problem well enough, and you don't just build one better tunnel. You change the economics and the timeline of underground construction everywhere, on every continent, across an industry that quietly moves hundreds of billions of dollars a year without most people ever noticing it exists. That's the claim behind this machine, and it's worth understanding exactly why it's such a hard problem, and exactly how novel this solution actually is. If you like videos like this, hit the like button. It takes a lot of research to put these together. And subscribe so you don't miss the next one. Here's where this goes. You'll learn why tunneling through unstable rock has stumped engineers for a century, what's actually happening mechanically inside this new machine that makes it different from anything built before, how it fits into China's already dominant position in global tunneling technology, what this could mean for the massive underground projects the world has planned over the next decade, how it stacks up against the established Western and Japanese manufacturers who've led this industry for generations, and where the real, unproven parts of this story still sit. Let's start with the problem itself. The problem that's been slowing tunnels down for a century. Underground construction has always come down to a fight between two very different tools, and neither one wins cleanly. The first is the tunnel boring machine, a rotating rock, producing a smooth, stable tunnel as it advances. The same basic principle whether the machine is boring a small utility tunnel or a full-scale rail line. TBMs are fast and safe in consistent ground conditions, and once one gets moving through favorable rock, it can advance dozens of meters a day with a relatively small crew. The catch is right there in that phrase, consistent ground conditions, because real geology is rarely consistent. When a TBM hits unexpectedly hard rock, unstable fault zones, or ground that shifts and deforms as pressure builds around the machine, it can slow to a crawl or get stuck entirely, sometimes for months, while engineers figure out how to free it, an outcome that has ended entire tunneling projects and cost overruns before. The second tool is traditional drilling and blasting. The older method, drill holes into the rock face, pack them with explosives, detonate in a controlled sequence, then clear the debris before starting again. It's a cycle that repeats, meter by meter, for the entire length of the tunnel. Drilling and blasting handles unpredictable, extremely hard, or highly fractured rock far better than a TBM can, because it doesn't rely on a single continuous mechanical process that can jam or fail partway through a difficult section. But it's slow by comparison, requires extensive safety precautions, and evacuation procedures for every single blast cycle, and needs a much larger, more specialized crew, working in shifts around the clock, all of which adds up to a meaningfully higher cost per meter of finished tunnel. For over a century, tunnel engineers have essentially had to pick their poison before a project even started, betting on which method would suit the geology better based on preliminary surveys, and then living with the wrong guess if conditions changed underground, which they very often do, sometimes within the span of a single day's progress. Deep tunnels through mountainous terrain are especially brutal in this regard, since a single tunnel route can pass through soft, crumbling rock in one stretch and dense, fractured granite a few hundred meters later, with no reliable way to know exactly where. The transition happens until the machine actually gets there and either grinds through smoothly or grinds to a halt. How the new machine actually works. The BBM's core idea is to stop forcing engineers to choose. CR6 describes it as a machine that can seamlessly alternate between three distinct modes: pre-blasting, followed by excavation, pre-excavation, followed by blasting, and full-face boring, switching between them based on what the rock face actually looks like in real time, without swapping out equipment or losing days to reconfiguration. In practice, that means a crew encountering an unexpected fault zone or a pocket of unusually hard rock doesn't have to halt the project, bring in a separate drilling and blasting crew and procedures. The same machine simply shifts its approach and keeps moving. The mechanism that makes this possible is a hollow cutterhead structure built around a central cutterhead, according to the research team at Tsinghua's State Key Laboratory of Hydroscience and Engineering. Instead of a single fixed cutting face like a conventional TBM, the hollow design allows different excavation approaches to operate through the same physical opening, letting operators shift strategy without physically reconfiguring the machine each time conditions change, the mechanical equivalent of a tool that can swap its own working end mid-task, rather than requiring a technician to walk over and manually change it. The system also includes retractable side cutters that adjust the excavation width as needed, useful both for shaping the tunnel and for maneuvering more easily back through sections that have already been completed, since a fixed-width machine can otherwise struggle to reverse or reposition itself in a tunnel it just carved. Because this machine sometimes needs to detonate explosives while still inside its own body, the engineering had to solve a problem no conventional TBM ever faces: protecting sensitive internal components, sensors, hydraulic systems, control electronics from repeated blast impacts delivered just meters away. The team added what they describe as an explosion-proof shield specifically to absorb that shock, a design challenge with essentially no direct precedent in the tunneling industry, since no prior machine has needed to survive its own onboard detonations as a routine part of normal operation. An adaptive telescopic tail shield supports different lining segment sizes, which matters enormously in unstable ground, since it allows the tunnel's structural lining to vary in diameter through sections affected by rock bursts or heavy deformation, rather than forcing a single rigid lining size through terrain that's anything but uniform along its length. Two independent conveyor belts round out the design, one handling excavated rock, the other managing construction aggregate, keeping material logistics moving even as the machine switches between cutting methods mid-tunnel, so that a change in excavation mode doesn't also mean a bottleneck in getting debris and materials in and out of the working face. Chinese officials have stated that the machine and its core components were developed with fully independent intellectual property, meaning this isn't a licensed foreign design adapted for local production. It's a from-scratch domestic engineering effort, built specifically to solve a problem Chinese tunneling firms have run into repeatedly on their own most difficult projects, from mountain rail corridors to the kind of deep, fault-riddled hydropower tunnels currently under construction in Tibet. Not China's first record breaker underground. This machine didn't appear out of nowhere. China has spent the last several years quietly building some of the largest and most capable tunneling equipment on the planet, and the BBM is really the latest entry in a pattern of escalating engineering ambition, rather than an isolated surprise that came from nowhere. Earlier this year, a shield machine working beneath the Yangtze River completed an underwater tunnel breakthrough for a new high-speed rail line, weighing in at roughly 4,000 tons with a 15.4-meter cutterhead, the largest diameter tunneling equipment ever used for high-speed rail construction anywhere in the world, achieving a single continuous underwater drive of more than 11 kilometers without surfacing once, a distance that would have been considered extraordinarily ambitious for underwater tunneling just a decade earlier, and that pushed the entire industry's understanding of how far a single continuous drive could realistically go. In Wuhan, a separate machine, nicknamed Zhengxianhao, was purpose-built for the largest underwater lake tunnel project in the region, with an integrated stone transportation and sorting system designed to keep excavation running continuously beneath the water table, automatically adjusting to different soil compositions as it advances, rather than requiring manual recalibration. And Chinese-built tunnel boring equipment isn't staying at home either. A Chinese-manufactured TBM is currently carving out Sydney's second major highway artery beneath the harbor, a 6.5-kilometer tunnel project, part of a broader pattern of Chinese tunneling firms exporting their equipment and expertise to markets that once relied almost exclusively on Western manufacturers for this exact class of heavy engineering equipment. That last point matters more than it might seem. The global tunnel boring machine market is valued at somewhere between $7 and $8.6 billion, expected to keep urban populations expand, and aging water and transit infrastructure across the developed world needs replacing. And for years it's been led by a small handful of specialized manufacturers, most notably Herrenknecht, the German firm that still holds somewhere between 22 and 30% of the global market, and remains the technology leader for the most demanding hard rock and variable ground projects worldwide, with a reputation built over decades of reliable performance on some of the world's most technically difficult tunnels, from the Gotthard Base Tunnel in Switzerland to major transit projects across the Middle East and India. Chinese manufacturers like CRI and Craig have spent the last decade closing that gap, not by matching a Herrenknecht feature for feature on every single machine, but by combining meaningfully lower costs with rapidly improving engineering capability, and by using China's own enormous domestic infrastructure pipeline, over 700 kilometers of operational urban metro track and counting, as a testing ground that few competitors anywhere else in the world can match in scale or frequency. Every new machine gets tested against real, varied Chinese geology almost immediately after leaving the factory, generating field data at a pace that smaller, more export-dependent manufacturers simply can't replicate as quickly, since they typically wait for a paying client's project to generate the same kind of real-world performance data. Why this could actually change how a lot gets built. Here's the part of this story that goes beyond one impressive machine. Nearly every category of major underground infrastructure runs into the exact soft rock burst, unpredictable geology problem this machine was designed around, which means the applications aren't limited to one niche corner of construction. They cut across almost the entire underground infrastructure economy. Urban metro systems are the most obvious example, since city tunneling routinely passes beneath a patchwork of different soil and rock conditions within the same short stretch of route, old riverbeds, filled-in wetlands, bedrock outcrops, sometimes all within a single kilometer of a planned route. Water and sewer infrastructure tunneling, a category researchers expect to grow significantly across Asia, Africa, and the Middle East as cities expand and existing systems age past their design life, faces the same variability underground, often in older urban cores where nobody has detailed geological records from a century or more ago, and every meter of progress carries genuine surprise. Mining operations, which often need to bore through some of the hardest and most unpredictable rock formations on the planet, could benefit even more directly, since mining tunnels frequently pass through exactly the kind of fractured, high-stress rock that causes the worst delays for conventional equipment. Delays that, in a commercial mining operation, translate directly into lost production revenue, measured in the millions of dollars per month. And then there's hydropower, which is where this technology connects most directly to some of the largest and most difficult tunneling projects happening anywhere on Earth right now. China's massive new hydropower project on the Yarlung River in Tibet requires boring tunnels up to 60 kilometers long, straight through active fault zones in the Himalayas. Exactly the kind of unpredictable, high-stress, rock-burst-prone environment that pushed engineers to develop something like the BBM in the first place. That project's own engineers have publicly described rock bursts and sudden soft rock deformation as among their single biggest construction risks, the same category of hazard. This new machine was explicitly designed to absorb and adapt to rather than simply endure. A machine that can genuinely adapt to sudden geological changes without stopping to swap equipment isn't just a nice efficiency upgrade for a project like that, it's close to a prerequisite for finishing it on anything resembling the current decade-long timeline. And it's not hard to imagine a future version of this exact machine, or one very much like it, eventually working inside that very mountain, tunneling through the same fault zones that have already produced earthquakes strong enough to worry engineers on the surface. The global race happening underneath our feet. None of this is happening in isolation from the rest of the world's tunneling industry, and it's worth being clear about where the real competition still stands. Herrenknecht isn't standing still either. Earlier this year, one of its machines broke through on the second tube of Switzerland's Gotthard Road tunnel, advancing nearly 4 kilometers through extremely hard rock at rates up to 32 meters a day, a genuinely impressive pace through some of the toughest alpine geology in Europe. And the company continues investing heavily in digital monitoring platforms like its Herrenknecht connected system, along with automated steering systems of its own aimed at closing exactly the kind of adaptability gap machines like the BBM are trying to address from a different engineering angle. The honest picture is less a story of China suddenly overtaking the rest of the world and more a story of a genuine three-way convergence. German engineering still leads on proven reliability and international trust for the most technically demanding projects, the kind of trust that takes decades of successful deployments to earn. Japanese manufacturers like Komatsu and Mitsubishi Heavy Industries continue to lead on precision engineering for specific applications, and Chinese firms are increasingly leading on raw innovation velocity, the speed at which entirely new machine concepts go from laboratory idea to a working prototype, rolling off a production line. The BBM is a clear example of that last pattern. Fewer than 2 years typically separate a major new tunneling concept from field deployment in China's current development cycle, a pace that Western manufacturers, working within more conservative certification and client approval processes built around decades of established liability and insurance frameworks, generally can't match, for better or worse, depending on how much weight you put on speed versus a longer track record of proven safety. What's still unproven? None of this means the BBM has already changed underground construction, and it's worth being direct about exactly how much is still unverified. The headline 30% efficiency improvement comes from laboratory testing, not from a completed real-world tunnel. Laboratory conditions can be controlled in ways that actual underground construction simply cannot, since a test bench doesn't have to contend with genuine groundwater. Infiltration, decades-old geological surveys that turn out to be wrong, or the sheer unpredictability of rock that's been under mountain-building pressure for millions of years. Plenty of promising tunneling innovations over the decades have looked excellent on a test bench before running into problems. Nobody anticipated, once they hit real, messy, unpredictable rock at scale, and the tunneling industry has a long enough memory of exactly that pattern to treat any new lab number with a healthy amount of caution before celebrating. The machine's first genuine test comes at a pumped storage hydropower station, a meaningful but still relatively contained demonstration project, not yet the kind of multi-year, multi-kilometer megatunnel that would truly stress test every mode this machine claims to handle across a genuinely diverse range of geological conditions. There's also a safety question baked into the core design that deserves scrutiny rather than a pass. Integrating live blasting operations into the same physical machine that houses sensitive boring components, sensors, and control systems is a genuinely novel engineering challenge, and the explosion-proof shielding described by the manufacturer will need years of real operational data across multiple projects and multiple crews before the industry can fully trust that repeated blast cycles won't degrade the machine's more delicate systems over time. The same way repeated small impacts can quietly fatigue metal components long before any single impact looks dangerous on its own. And switching between 3 distinct operating modes adds real mechanical and procedural complexity compared to a single purpose machine, complexity that has to be managed correctly by every operating crew on every project for the promised efficiency. Gains to actually materialize rather than get eaten up by additional training time, operator error during the learning curve, and the extra maintenance overhead that typically comes with any machine doing more than one job. What happens next will be decided underground, not in a press release. If the BBM performs at the pumped storage demonstration site the way it performed in the lab, the next logical step is deployment on a genuinely difficult mega project, something like the fault-riddled tunnels beneath the Himalayas or a similarly unforgiving mining or metro route, where the real payoff of adaptive mode-switching excavation would show up clearly in months saved and dollars not spent on stalled equipment, rather than in a laboratory percentage quoted in a press release. Until that happens, this remains a genuinely impressive, genuinely novel machine with a promising number attached to it, not yet a proven revolution in how the world builds underground. If this kept you watching to the end, hit like, subscribe, and turn on notifications so you catch the next one. Here's a question for you. Do you think machines like this will meaningfully speed up the massive tunneling projects the world has planned over the next decade? Or is a 30% lab number the kind of claim that tends to shrink once it meets real rock, real weather, and real deadlines? Let me know in the comments.